somewhere out past Mars, past the asteroids, circling a planet so massive it could swallow 1,000 Earths. There is a small moon with a face that should not exist. Its surface carries no scars, no craters, nothing that shows its age at all. And yet this little world is older than nearly everything else we can see tonight. Something down inside it refuses to go quiet, no matter how long anyone watches. Spacecraft that flew past it, decades apart, both came home with pictures of a body still being rebuilt over and over in real time. Nobody expected that. Nobody, at first, even believed it. And even now, scientists are still arguing about exactly what is happening beneath that restless surface. Stay with us, and let's find out together. If a moon that refuses to grow old is the kind of thing that keeps you curious, a like and a subscribe helps this little channel keep exploring worlds like it with you. Get comfortable, settle in. In 3, 2, 1, liftoff. Somewhere in the crowded space around Jupiter, closer to the giant planet than any of its other large moons, there circles a small world that, by every reasonable expectation, should be quiet, cold, and still. It is barely larger than our own moon. A modest ball of rock, a little over 2,200 miles across, tucked in tight against a planet more than 1,000 times its size. Small worlds like this are supposed to have finished their story a long time ago. They form, they cool, and they settle into a long, unremarkable retirement, their surfaces slowly filling with the pockmarks and scars of billions of years' worth of wandering debris. That is the pattern almost everywhere else we have looked. It is not the pattern here. This moon is called Io, and from a distance, before anyone understood what they were truly looking at, it appeared almost decorative, its surface washed in shades of butter yellow, rust orange, and a deep, burnt red, broken up by patches so dark they looked like scorch marks left behind on a stovetop. Nowhere on that colorful surface, not in a single image taken by a single spacecraft in the decades since anyone first looked closely, has anybody ever found an impact crater. Not one. Every other solid surface we have ever photographed up close wears its history openly. Io wears no such record at all. Something on this small moon keeps erasing the past almost as fast as it is written, and in 1979, that something announced itself to a young engineer at a laboratory in Southern California who had not been looking for it in the slightest. Her name was Linda Morabito, and by the time Jupiter came into view through Voyager's cameras, she had spent years working her way up at the Jet Propulsion Laboratory, starting as a young student employee, taking summer work while she pursued her degree in astronomy at the University of Southern California, and rising eventually to the title of cognizant engineer over the laboratory's optical navigation image processing system. Her job on the mission had nothing to do with volcanoes or moons for their own sake. A spacecraft moving hundreds of millions of miles from home cannot simply check a map. Instead, navigators photograph a moon against the fixed pattern of background stars, measure exactly where that moon appears to sit relative to those stars, and use the resulting geometry to calculate, with remarkable precision, exactly where the spacecraft itself must be at that moment. It is patient, unglamorous work, almost entirely invisible to the public, and utterly essential to keeping a mission on course across the solar system. On the 5th of March, 1979, the spacecraft she helped guide, a robotic explorer named Voyager 1, made its closest pass by Jupiter, and in the days that followed, it turned its cameras toward Io once more, this time purely for navigation purposes, taking a long exposure photograph meant to catch faint background stars rather than the moon itself. The image itself was taken 3 days after that closest approach, and working through it at her desk the following day, Morabito increased the contrast to bring out those dim stars, and something appeared that had no business being there. A bright, curved shape rising off the edge of the moon, arching outward like a parasol caught mid-toss in the wind. She spent the rest of that day ruling out every ordinary explanation before concluding, by evening, that she was looking at something that had never once been confirmed anywhere beyond Earth. An active volcanic eruption, caught in the act, on another world entirely. Nothing about Jupiter's system was entirely unknown before that moment, and it is worth understanding why nobody had caught this sooner. 2 earlier spacecraft, Pioneer 10 and Pioneer 11, had each swept past the giant planet several years earlier, in 1973 and 1974, sending back the first close-up glimpses of Jupiter and its largest moons. Those 2 pioneering spacecraft, however, carried simpler instruments, built for a mission whose main goal was proving that a spacecraft could survive the punishing radiation surrounding Jupiter at all. And their cameras lacked the resolution and sensitivity needed to catch anything as fine and as fleeting as a volcanic plume rising against the blackness of space. Nobody could fault them for missing it. Voyager 1, arriving 5 years later, carried a far more capable set of instruments, part of a broader leap forward in spacecraft technology during that decade, and it was that improvement, as much as any stroke of luck, that finally brought Io's secret into view. The technique Morabito used to bring that shape into view was itself a small feat of the era's technology, and it is worth pausing on because it explains how something this dramatic could hide in plain sight for 3 full days. A raw navigation image, fresh off the spacecraft, tends to look almost featureless, its brightness compressed into a narrow band so that neither the faintest nor the brightest parts of the frame are lost in transmission across hundreds of millions of miles. By artificially stretching that narrow band of brightness across the full range a display could show, a routine step navigators used to coax faint background stars out of the darkness, previously invisible detail can suddenly leap into view. It was this same ordinary procedure, applied to an ordinary image, taken for an entirely different purpose, that revealed the plume rising off Io's edge. Nobody had built that camera or designed that processing technique with Volcanoes anywhere in mind. Before she would even raise the possibility with anyone else, Morabito worked the problem the way any careful engineer would, checking with colleagues who understood the camera intimately about the chance of a stray reflection or a flaw in the optics, and checking the known positions of Io's neighboring moons, in case some previously uncatalogued satellite had simply drifted behind Io at exactly the wrong instant, catching sunlight at a strange angle. Neither explanation survived the scrutiny. In 1979, astronomers had catalogued only a small handful of moons orbiting Jupiter, a far shorter list than the many dozens that would eventually be found using telescopes and techniques not yet available at the time. Ruling out a stray, previously unknown satellite was therefore a real possibility worth checking carefully, not an idle formality, and Morabito and her colleagues worked through the geometry with exactly that seriousness. Nothing in the known positions of Io's neighbors lined up with what the image showed. Whatever was rising off that dark limb was attached to Io itself. The image processing work Morabito performed that week took place at consoles surrounded by the particular hum and clatter of 1970s computing, rooms filled with reel-to-reel tape drives and black and white display terminals, rendering images, piece by piece, from data that had crossed hundreds of millions of miles as a stream of radio signals before ever becoming a picture a human eye could interpret. It was demanding, highly technical work, and Morabito was one of a relatively small number of engineers trusted with a role that combined astronomy, computer science, and the exacting discipline of spacecraft navigation all at once. It was precisely that combination of skills, sharpened through years of routine, careful image analysis, that put her in a position to notice something so easy to overlook. The mood inside the laboratory that week is worth sitting with for a moment, because it says as much about the nature of discovery as the plume itself does. Voyager 1's images were arriving in a steady, demanding stream, and the navigation frames Morabito was working through were, by the standards of the mission, considered low priority, background bookkeeping compared to the striking, headline-worthy photographs of Jupiter's storms and its brighter, icier moons that were commanding most of the attention that week. Nobody was hovering over her shoulder, expecting a discovery from that particular stack of pictures. There was no bank of television cameras trained on her console, no crowd gathering the moment the anomaly appeared on her screen. She simply sat with the problem, alone at first, until she had worked through it carefully enough to trust her own eyes. Among the thousands of images the spacecraft transmitted home during that single encounter, the vast majority were never intended to draw much scrutiny at all, once their narrow navigational purpose had been served. It would have been entirely reasonable for the picture containing Io's plume to be processed, filed, and forgotten, one unremarkable frame among many, its true content never noticed by anyone. That it was not is due entirely to the particular combination of a routine technical step applied out of habit and a careful engineer willing to look twice at what that step revealed. It would be hard to overstate how unlikely her conclusion felt, even once she began sharing it with others, because it ran against a basic and, until that week, thoroughly reasonable principle of planetary science. A world's internal heat comes from a small number of familiar sources, the leftover warmth of its own violent formation, slowly leaking away over billions of years, and the ongoing, gradual decay of radioactive elements buried in its interior, a process that runs down like any fuel supply eventually does. Both sources scale, roughly, with a world's size, the way a large pot of soup stays warm on the counter far longer than a single spoonful does. By that reasoning, a moon as small as Io, its interior no larger than many of the asteroids and minor worlds scattered elsewhere in the solar system, should have gone cold within its first billion years of existence, if not sooner. Whatever was keeping this particular moon's interior molten billions of years after its formation could not be explained by either of those two familiar sources acting alone. It had to be something else, something involving forces reaching in from outside the moon itself, rather than heat trapped inside it from the very beginning. And yet Morabito was not imagining things. Once she and her colleagues were confident in what they were seeing, they went back through every picture Voyager 1 had already taken on its way past Jupiter, this time knowing precisely what shape to look for, and found the same telltale form in several more of them. By the end of that review, a single flyby that nobody had expected to reveal anything of the kind had captured 8 separate active eruptions, spread across a small moon that, only days earlier, had been treated as one of the less interesting stops on the itinerary. What struck scientists almost as much as the plumes themselves was where they were found. Those 8 eruptions were not clustered together in one corner of Io, the way a single unlucky patch of unusually thin crust might produce a scattering of nearby vents. They turned up on opposite sides of the little moon, in images taken of entirely different regions. Whatever was driving this activity did not look like a local accident. It looked, even in that very first flyby, like a condition affecting the moon as a whole. The plume Morabito herself had found rose from a dark, irregular patch that scientists would later name Pele, after the Hawaiian deity said to preside over volcanoes and fire, a name that would go on to mark one of the most persistently active spots on the entire moon for decades afterward. Morabito herself would later describe that morning simply as the stuff of dreams, the feeling of seeing something that, in all likelihood, no human being had ever laid eyes on before. Beyond the plumes themselves, the images Voyager 1 sent home revealed a landscape unlike anything catalogued elsewhere in the solar system, a patchwork of sulfur yellows and burnt oranges interrupted by dark, irregular stains where fresh material had clearly flowed and cooled, and by jagged shadows cast by peaks and ridges whose true scale scientists would only work out with time. There was no single dominant terrain type the way there might be on a more ordinary moon, no broad, uniform plains or simple cratered highlands. Instead, the surface looked assembled almost haphazardly, one region overprinted onto another, exactly the kind of appearance one would expect from a world being rebuilt over and over, rather than one quietly aging in place. The darkest of those patches, scientists would come to suspect, marked places where fresh material had only just reached the surface and had not yet had time to react and cool into the brighter yellows and oranges surrounding it, a visual clock of sorts, written across the moon in shades of black, fading slowly toward gold. Sulfur is an unusually theatrical element in this regard. Depending on the temperature at which it cools and solidifies, it can take on almost any shade along a spectrum, from pale yellow through orange and red to a near black, which is part of why Io's surface reads less like a single coherent landscape and more like a painter's palette left out in the open. A single eruption, cooling unevenly as it spreads and settles, can produce several of those colors within the same small stretch of ground, layered one atop another as later flows spill across older ones. Long before anyone understood what was driving Io's volcanism, that simple chemical property was already writing the moon's entire, ever-changing color scheme across its surface for any passing spacecraft to photograph. What makes this discovery even more remarkable is that, in a strict sense, nobody ought to have been caught entirely by surprise. 3 days before Voyager 1 made its closest approach to Io, a trio of researchers named Stanton Peele, Patrick Casson, and Ray Reynolds had published a paper built almost entirely on mathematics, with no telescope or spacecraft involved in the work at all, arguing that the particular gravitational relationship between Io and its neighboring moons ought to generate enough internal heat to melt a substantial portion of the little moon's interior. They went a step further still, suggesting in their own paper that the consequences of such a molten interior might well be visible in whatever pictures Voyager 1 managed to send home from its encounter. Peele worked at the University of California, Santa Barbara, while Casson and Reynolds were both based at NASA's Ames Research Center in Northern California, and none of the three had any direct role in the Voyager mission itself. Their paper had grown out of a narrower question. What effect would the particular, precisely timed gravitational pull of Io's neighboring moons have on Io's orbit, and in turn on Io's interior, over the course of each trip around Jupiter? Working through that question with nothing but mathematics, they concluded that the effect would be far from trivial, large enough, in fact, to keep a substantial portion of the little moon's interior molten indefinitely. It is a rare thing in the history of any science for a prediction that specific, made that close to the event it concerns, to be confirmed so quickly and so dramatically. The theorists had worked out the arithmetic sitting at their desks, using nothing more than an understanding of orbits and gravity. The spacecraft, arriving only days later, supplied the photograph. Less than a single week separated the publication of that paper from the moment Linda Morabito found what it had promised would be there. To understand why that prediction carried so much weight, it helps to step back and place this small moon properly within its surroundings. Io is the innermost of the 4 large moons that circle Jupiter, a family of worlds first spotted through a telescope by the Italian astronomer Galileo Galilei back in January of 1610, and which still carry his name today as the Galilean moons. To Galileo, watching through one of the earliest telescopes ever pointed at the night sky, these 4 moons appeared as nothing more than faint points of light, shifting position from night to night in a way that convinced him correctly that they were orbiting Jupiter rather than simply passing near it, evidence he used to help argue that not everything in the heavens circled the Earth. It was a monumental observation in its own right, one of the pieces of evidence that helped reshape humanity's understanding of its place in the universe. But a telescope from that era, however revolutionary, could never have shown him anything of what those 4 points of light actually looked like up close, let alone what might be happening on or beneath their surfaces. That would take nearly 370 more years, and a spacecraft launched from the very world Galileo had helped remove from the center of everything. Of the 4 Galilean moons, Io sits closest to the giant planet it orbits, so close that it completes one full circuit around Jupiter in just 42.5 hours, less time than a long holiday weekend back here on Earth. It is a small world by planetary standards, a little over 2,200 miles across, only slightly larger than our own moon, and equal to roughly 1/4 of the width of Earth itself. It shares its neighborhood with 3 other large worlds: Europa, a smooth, ice-covered moon slightly smaller than our own; Ganymede, the largest moon in the entire solar system, bigger even than the planet Mercury; and Callisto, a heavily cratered world drifting in a wider, quieter orbit farther from Jupiter's immediate grip. Of the 4, only Io shows no impact scars whatsoever, and only Io burns this hot on the inside. Its 3 neighbors would, it would eventually turn out, have far more to do with that difference than anyone suspected in 1979. It helps, too, to picture the scale of the world Io calls home. Jupiter is, by a wide margin, the largest planet in our solar system, so massive that every other planet combined could be tucked inside it with room left over. Seen from Io's own sky, Jupiter would not simply be a bright point of light the way it appears from Earth, but an enormous banded sphere filling a wide swath of the heavens, its clouds visibly churning to anyone who could somehow stand safely on Io's surface and look up. Io orbits well within the region where Jupiter's gravity utterly dominates everything nearby. Measured against the sheer size of the planet it circles, Io hugs Jupiter roughly 10 times more tightly, in proportion, than our own moon hugs Earth, circling a world so large that its gravitational grip on nearby objects is correspondingly immense. Io's neighborhood is not a gentle one in other respects either. Jupiter's enormous magnetic field, far stronger than Earth's own, traps charged particles into radiation belts, intense enough to damage sensitive electronics, a hazard every spacecraft passing through the inner Jupiter system has had to be engineered to withstand. Io itself orbits directly inside the thick of that radiation environment, closer to Jupiter than any other large moon, exposed constantly to conditions far harsher than anything experienced by worlds farther out in the same system. It is against this towering, difficult backdrop that Io's own peculiar behavior has to be understood. A small moon squeezed by gravity on one hand and bathed in radiation on the other, long before anyone understood that this same crowded, demanding neighborhood was also the very thing keeping its interior so relentlessly warm. The spacecraft responsible for finding all of this had already been traveling for a year and a half by the time it reached Jupiter, launched from Earth in early September of 1977 as one of a pair, alongside a twin craft that would go on to visit Jupiter, Saturn, Uranus, and Neptune in turn. Over the following decade, the two spacecraft were taking advantage of a rare alignment of the outer planets, one that would not repeat again for well over a century, allowing a single mission to use the gravity of each planet it passed to help fling it onward toward the next. Reaching the outer solar system at all was, even by the standards of its era, an extraordinary technical achievement, a project that captured public imagination the way space missions of that decade routinely did, following as it did on the heels of the moon landings less than 10 years earlier. For a public that had watched astronauts walk on the moon broadcast live into their own living rooms, the Voyager missions carried some of that same sense of occasion. Newspapers and evening broadcasts covered each flyby as it happened, and the discovery of an active volcano on a moon of Jupiter, a genuinely novel finding rather than simply another set of closer photographs, was the kind of story that traveled well beyond the scientific journals, reaching ordinary households the same way the moon landing had, as a small, shared moment of looking outward together. Jupiter's system of moons was the first great destination on that longer journey, and scientists had trained most of their attention on the giant planet itself and on its larger, icier moons. Io, small, rocky, and tucked in close to its parent planet, was expected to be a relatively minor character in the encounter, useful mainly as a navigational reference point rather than a subject worth studying in its own right. That expectation collapsed within days of the spacecraft's arrival. For the scientists following the encounter from Mission Control, the discovery landed with the force of a genuine shock once word of it spread. Until that week, the working assumption inside planetary science had been that a moon this size, this far from the warmth of the sun, and this cold on its outer surface, would be geologically finished, a leftover from the solar system's formation, with nothing left to do but sit quietly and gather the occasional scar from a passing piece of debris. Instead, here was direct photographic proof of an eruption caught in progress, a plume of fine material thrown roughly 170 miles above the surface, arcing back down under its own weight the way water falls from a fountain, except that what fell here was not water at all, but tiny particles of sulfur and its many compounds, the very same family of elements responsible for painting the moon's surface in those startling yellows, oranges, and reds. Edward Stone, the mission's project scientist, was brought in almost as soon as Morabito and her colleagues had ruled out the ordinary explanations, and he recognized immediately what he was looking at. Word moved quickly through the rest of the science team in the way it moved at a place like the Jet Propulsion Laboratory in that era, through hurried phone calls between offices and people leaving their own desks to see for themselves, and instruments across the spacecraft were redirected to gather whatever additional confirmation they could. Word of the discovery also reached the team preparing Voyager 1's twin, Voyager 2, in time to matter. That second spacecraft was still 4 months from its own closest approach to Jupiter when Morabito made her find, and mission planners used the time remaining to adjust its observation schedule, making sure it would take a much closer look at Io and its eruptions when its turn came in July of that same year. What had begun as an accidental discovery buried in a low-priority navigation photograph had, within months, reshaped the plans of an entire second spacecraft, already in flight and already committed to its course, its instruments now aimed with new purpose at a moon nobody had expected to matter this much. A moon that had, only days earlier, been considered one of the more forgettable stops on the itinerary, suddenly became the single most talked about object of the entire encounter, and news of the discovery rippled outward from the laboratory almost as fast as the plumes themselves seemed to rise and fall. A moon that had been catalogued for nearly 370 years, ever since Galileo first noticed it as a faint point of light beside Jupiter, was abruptly the site of the first confirmed volcanic eruption ever witnessed anywhere beyond Earth. Assumptions that had treated small, rocky moons as settled, finished worlds needed to be reconsidered from the ground up. If a body this size, this far from any obvious source of internal warmth, could still be this restless, then the old idea that size alone determined a world's geological fate was, at the very least, incomplete. In the decades since, some planetary scientists have gone so far as to call this the single most significant discovery to come out of the entire history of the laboratory's planetary exploration program, a striking claim given how much that same laboratory has since found across the solar system. Whether or not it holds that exact distinction, it is hard to argue with what it set in motion, an entirely new category of geological activity, confirmed for the first time anywhere beyond our own planet, found not by a telescope built for the purpose, or a mission designed to search for it, but by one careful engineer looking closely at a photograph nobody else was watching that day. And the puzzle only grew stranger the longer scientists sat with it. A moon squeezed this close to Jupiter should, if anything, have been battered more severely by impacts over its lifetime than worlds farther out, not less, since objects falling toward a massive planet tend to pick up additional speed as they fall, making any eventual collision more violent rather than gentler. By every reasonable expectation, Io ought to have been at least as heavily cratered as its neighbors, if not more so. Instead, it showed none at all. Whatever process was resurfacing this moon was not merely keeping pace with the ordinary wear of passing debris. It was erasing that history so thoroughly and so continuously that not a single scar had survived to be photographed, not from 1,000 years ago, not from 1,000,000 years ago, not from any point in the moon's long existence that anyone could identify. That fact alone, quite apart from the plume itself, told scientists that whatever they were dealing with here was not an occasional or passing event. It looked, instead, like a permanent condition, a fixed feature of how this particular moon simply existed. Io would not be visited only once. In the years and decades that followed that first startling encounter, other spacecraft would return again and again to look more closely at this small, restless moon, drawn back by exactly the puzzle Voyager 1 had uncovered almost by accident while it was busy looking for background stars. Each return visit would add new layers of detail, new questions, and new arguments among scientists about what was truly happening beneath that endlessly repainted surface. Arguments that, in some respects, continue even now, decades later. But all of that lay years ahead. In 1979, there was only the plume itself, rising silently over Io's horizon in a handful of overexposed photographs, and the enormous, still unanswered question of what could possibly be powering it. The answer, when scientists finally worked it out in full, had almost nothing to do with Io itself, and everything to do with the company it keeps. That single, overexposed photograph from 1979 was proof that something extraordinary was happening. It was not, on its own, an explanation of why. To understand how a small moon barely larger than our own could stay molten for as long as it has, it helps to start with something far more familiar: the ordinary rise and fall of the tides along any coastline here on Earth. Twice a day, along nearly every shoreline on the planet, the ocean rises and falls, pulled mainly by the gravity of the moon as it passes overhead, with a smaller contribution from the sun's own gravity layered on top. That familiar rhythm has a simple cause. The side of the Earth closest to the moon feels a slightly stronger pull than the side farthest away, and that difference in pull stretches the oceans, ever so slightly, into a bulge that trails the moon's position as the Earth spins beneath it. Solid rock responds to the very same kind of pull, only far less visibly. The ground beneath your feet rises and falls by a small fraction of an inch every single day, tugged by that same lunar gravity, though almost nobody ever notices it happening. Earth and its own moon offer a helpful parallel here, precisely because the same underlying physics, tidal energy being exchanged between two orbiting bodies, produces a strikingly different result. As Earth's oceans rise and fall under the moon's pull, friction between the moving water and the ocean floor drains a small amount of energy out of the Earth-Moon system with every single tide. That lost energy has to go somewhere too, and in this case, it slowly pushes the moon a little farther away from Earth, while gradually slowing Earth's own rotation, a process measured today at a rate of roughly 1.5 inches of added distance every single year, confirmed through decades of extraordinarily precise laser measurements, bounced off reflectors, astronauts left behind on the lunar surface. Left running for long enough, this same kind of tidal drain in the Earth-Moon system gently separates the two bodies and calms their relationship down over time. Io's situation produces the opposite outcome, not because the physics is different, but because the arrangement of bodies involved is different. Europa and Ganymede's timed tugging keeps refilling the very eccentricity that tidal friction would otherwise drain away. So instead of settling down the way Earth and the Moon slowly are, Io stays trapped in the same restless cycle indefinitely, its energy converted into heat, rather than into a gradually widening orbit. Scientists have a specific name for energy lost this way, converted from orbital motion into heat or displacement through repeated flexing, tidal dissipation. It is the same general process at work, whether the result is a slowly receding moon, as it is for Earth, or a moon kept perpetually molten, as it is for Io. What differs between the two cases is not the physics itself, but the surrounding circumstances, whether anything is present to keep replenishing the very stretching that dissipation would otherwise wear away. Jupiter performs the same trick on Io, only on a far grander scale. Jupiter is so much more massive than our moon, and Io orbits so much closer to Jupiter than our moon orbits Earth, that the tidal pull Jupiter exerts on Io dwarfs anything the moon manages on our own oceans. Io's solid body responds to that pull just as Earth's oceans do, stretching very slightly into an elongated shape pointed toward Jupiter, a bulge raised not in water but in solid rock. If Io's path around Jupiter were a perfect circle, that bulge would stay the same size and the same shape indefinitely, always pointed in the same direction relative to Jupiter, and the story would more or less end there. A permanently stretched moon, no more remarkable than any other tidally locked satellite in the solar system. Left to itself, an orbit like this tends to become more circular over time, not less. Each time Io's tidal bulge stretches and relaxes, a very small amount of the orbit's own energy bleeds away, and losing energy from an elliptical orbit generally has the effect of rounding it out. the way a wobbling, spinning top gradually settles into a smoother, steadier spin as it loses energy to friction with the air and the surface beneath it. Left alone for long enough, that slow rounding should have smoothed Io's path into a nearly perfect circle within a comparatively short span of the moon's history, and once truly circular, the tidal bulge would stop growing and shrinking altogether, freezing into a fixed shape that generates no further heat at all. But Io's orbit is not a circle, and understanding why requires meeting its neighbors properly. Io shares its orbit around Jupiter with two other large moons, Europa and Ganymede, both of which pull on Io with their own gravity every time their paths draw close. Left entirely to themselves, over enough time, the ordinary stretching and relaxing of a tidal bulge tends to smooth an orbit out, rounding it into a neat circle. Io's orbit should have circularized long ago, by the same reasoning that applies to any orbit losing energy this way. It never has, because Europa and Ganymede keep interrupting that process in a very particular, precisely timed way. More than a century before Peale, Casson, and Reynolds ever wrote their own paper connecting this arrangement to Io's heat, a French mathematician named Pierre-Simon Laplace had already worked out the underlying relationship among these three moons, using nothing but pen, paper, and an extraordinary command of orbital mechanics. For every 4 trips Io makes around Jupiter, Europa completes almost exactly 2, and Ganymede completes almost exactly 1. That precise, repeating ratio is what astronomers now call the Laplace resonance, and it is the reason the three moons keep meeting each other, orbit after orbit, at nearly the same points along their paths, rather than drifting past one another at random. Laplace is remembered today as one of the towering figures of that era's mathematics and astronomy, a man whose work on the mechanics of the solar system filled volumes and touched nearly every corner of celestial motion then known. His analysis of Io, Europa, and Ganymede's shared rhythm was, in his own time, a purely mathematical curiosity, a demonstration that their orbital periods were locked together with remarkable precision, with no hint that the arrangement might also be quietly cooking one of those three moons from the inside. That connection would wait for the 20th century, and for scientists willing to ask not just how the moons moved, but what that movement might be doing to them. It can help to picture the three moons as musicians keeping a shared beat rather than playing independently, each one completing its own distinct part, Io fast, Ganymede slow, Europa in between, yet always returning to the same relative positions at the same predictable points, orbit after orbit, the way three drummers playing patterns of different lengths will still find their beats lining up again after a fixed, repeating number of measures. Think, too, of pushing a child on a playground swing. Push at random moments, with no regard for the swing's own natural rhythm, and your pushes mostly cancel each other out, doing little to change how high the child goes. Time your pushes to match the swing's own back and forth rhythm, however, arriving at exactly the right instant in every cycle, and even a gentle push keeps the swing going indefinitely, or even sends it higher, instead of letting it settle down to hang straight and still. Europa and Ganymede act on Io's orbit in exactly this second way. Because their orbital periods line up with Io's so precisely, their gravitational tugs arrive at nearly the same point in Io's orbit every single time, reinforcing the same stretch in the same direction over and over, rather than smoothing it away. The natural tendency of Io's orbit to relax into a circle never gets the chance to finish. Europa and Ganymede keep pushing at exactly the right moment, cycle after cycle, holding Io's path, stretched into an ellipse instead. There is something almost self-correcting about the whole arrangement, too. Should Io's orbit ever drift slightly out of step with Europa's or Ganymede's, the same gravitational tugging that maintains the resonance tends to nudge it back into line, the way a well-timed push on a swing corrects for a slightly mistimed one on the very next pass. The resonance does not require perfect precision at every single instant. It only requires that any small drift get corrected before it accumulates into something larger, and over the vast span of time these three moons have shared their orbits, that correction has held. Europa and Ganymede do not need to be especially close to Io for this arrangement to matter. What matters is the timing. Ganymede, the largest of the three moons and the most massive, contributes a smaller tug than Io feels from Jupiter itself, but a tug delivered at precisely the same point in Io's orbit, cycle after cycle, adds up to something significant over time. Europa, orbiting between Io and Ganymede, plays a similar role on a slightly different rhythm. Neither moon needs to overpower Jupiter's gravity to matter here. They only need to arrive, again and again, exactly when their pull will do the most to keep Io's orbit from relaxing. Picture the other two moons for a moment, since they will keep reappearing throughout this story without ever once touching Io directly. Europa is smooth, almost polished looking from a distance, its icy shell webbed with long, dark cracks that suggest a frozen surface hiding something less frozen underneath. Ganymede, larger still, shows a mix of ancient, heavily cratered terrain alongside younger regions grooved and furrowed like a plowed field, and stands alone among every moon in the solar system in having a magnetic field of its own, generated deep within it, much the way Earth's is generated within our own planet. Neither world looks anything like Io. Neither one needs to. An elliptical orbit means Io's distance from Jupiter is never constant. At its closest approach, Io swings in nearer to the giant planet. At its farthest point, it drifts a bit farther out, all within the same 42.5-hour circuit. The change in distance between those 2 points, measured against the sheer scale of the orbit as a whole, is not large. It is a small deviation from a perfect circle, easy to overlook on a diagram drawn to scale. But Jupiter's gravity is so overwhelming at this distance, and its pull weakens or strengthens so sharply with even modest changes in distance, that this small deviation is more than enough to matter. A slight difference in distance translates into a very real difference in pulling force, and that difference is exactly what keeps reshaping Io's tidal bulge, growing larger as Io swings in close and shrinking back down as it swings back out, orbit after orbit, rather than allowing that bulge to settle into anything fixed. If it were possible to watch that change directly, rather than infer it from years of careful measurement, the moon would appear to breathe, ever so slightly, with every single orbit, swelling almost imperceptibly toward Jupiter as it swings in close, relaxing back as it swings away, then swelling again on the very next pass, never truly still. No human eye has ever seen this happen directly. The changes involved are far too small to notice by looking, even from close range, and far too gradual to register as motion in the way a beating heart or a breathing chest might. It shows up only in the numbers, in years of precise tracking of Io's position and shape, and yet it is happening constantly, every 42.5 hours. Whether or not anyone is watching it happen at all, an observer stationed safely near Io, watching Jupiter through an entire orbit, would notice the giant planet itself subtly changing size in the sky, swelling almost imperceptibly larger as Io swings in toward its closest approach, then shrinking back as it drifts out toward its farthest point, repeating that same slow swell and shrink every 42.5 hours without variation. It is the same changing distance responsible for the changing tidal pull, made visible in the simplest way imaginable, a planet that never quite holds still in size, even though its actual bulk never changes at all. This is the crucial difference between Io and a moon whose bulge simply sits still, and it is where the heat finally enters the story. Flexing solid rock, even by a small amount, is not free. Some of the energy involved in stretching and relaxing a material is lost along the way, converted into heat through internal friction, in much the same way that working a lump of bread dough over and over between your hands leaves it noticeably warmer than when you started, even though nothing was ever heated on a stove. Io's rock is kneaded in exactly this sense, squeezed toward Jupiter and released, squeezed and released again on every single orbit. Because that circuit takes only 42.5 hours to complete, Io experiences this entire squeeze and release cycle roughly 200 separate times within a single Earth year, far more often than most familiar cycles here at home repeat. A moon barely larger than our own is needed, in effect, roughly 200 times over every single year, and has been for as long as this particular arrangement of moons has existed. Each cycle generates only a small amount of heat on its own, repeated without pause, orbit after orbit after orbit. That small amount adds up into something enormous. Enough heat, continuously renewed, to keep a substantial portion of Io's interior molten rather than solid. Pound for pound, the heat Io generates this way dwarfs what a body its size would ordinarily produce from the leftover warmth of its own formation and the slow decay of radioactive elements alone, the two sources that power geological activity on most rocky worlds. Those two familiar sources scale with a world size and fade steadily over billions of years, which is exactly why Mercury, roughly comparable in size to Io, and our own moon, slightly smaller still, both went geologically quiet long ago. Io, squeezed by an orbit gravity itself refuses to let settle, simply never got the chance to follow that same quiet path. Heat generated this deep inside a moon cannot simply stay there forever. It has to go somewhere, and the most direct path available to it is upward, through cracks and weak points in Io's crust, carrying molten rock along with it toward the surface. Every plume Voyager 1 photographed, every eruption confirmed since, traces back to this same underlying process. Rock melted by friction, born of an orbit that gravity itself will not allow to settle down, forcing its way upward and out, because there is, quite simply, nowhere else for all that energy to go. Exactly where that upward path breaks through depends on where Io's crust happens to be thinnest or most fractured at any given time, which is part of why the moon's volcanic centers are scattered so widely rather than clustered in one predictable location. A crack that offers an easy path today may seal itself with cooling rock tomorrow, forcing the next surge of molten material to find a different route entirely. Over the moon's long history, that shifting, unpredictable search for a way out is part of what has left virtually no square mile of Io's surface untouched by an eruption of one kind or another. Earth handles its own internal heat very differently. Our planet's crust is broken into large, rigid plates that drift slowly across the surface over millions of years, occasionally colliding, sliding past one another, or pulling apart, releasing heat gradually along their edges through volcanoes and earthquakes concentrated in fairly predictable belts. Io has nothing resembling this system. Its crust behaves less like a set of rigid plates and more like a lid being repeatedly punctured from below, patched and punctured again somewhere new, with no large-scale drifting or collision involved at all. Where Earth manages its internal heat through slow, organized motion measured in inches per year, Io simply erupts, over and over, wherever the pressure happens to find its easiest way out. Scientists do not have to guess at how much of this heat actually reaches Io's surface. Every hot spot, every active lava flow, every lake like the one inside Loki Patera glows in infrared light, wavelengths invisible to human eyes, but easily captured by instruments designed to detect heat rather than ordinary visible light. By measuring that infrared glow across the entire moon, adding up the contribution from every detected hotspot, scientists can arrive at a genuine, physical measurement of Io's total heat output, rather than relying on theory alone. That total, once properly measured, turns out to be enormous, a number substantial enough on its own to settle any remaining doubt that the mechanism described here is doing exactly the work Peel, Casson, and Reynolds once predicted it might. Ground-based observatories have kept up exactly this kind of infrared monitoring for decades now, joined by every spacecraft that has passed close enough to Io to point an instrument at it, building a record patient enough to separate a single, unusual week from a genuine, sustained pattern. Callisto offers a useful contrast, precisely because it sits outside this arrangement, orbiting farther from Jupiter, and uninvolved in the resonance linking its three inner siblings. Callisto's orbit has been left free to do exactly what orbits left alone tend to do: settle down. Its path around Jupiter is close to a true circle, its tidal bulge, such as it is, essentially fixed in place rather than constantly reshaped. Callisto's surface shows the result plainly. It is the most heavily cratered of the 4 Galilean moons, its face carrying a visible record of billions of years of passing debris, precisely because nothing inside Callisto has been kept churning and molten the way Io's interior has. Where Io shows no scars at all, Callisto shows nothing but. Standing the two moons side by side, close enough in size to be cousins, is as clear a demonstration as the solar system offers of what a shared resonance can do to one world and leave entirely untouched in another. None of this was inevitable, either. A relationship this precise, 3 separate orbits locking together and staying locked for as long as the moons themselves have existed, is not the outcome one would expect from 3 worlds evolving independently by chance. Left to develop without whatever process first drew their orbital periods into this particular ratio, Io, Europa, and Ganymede might easily have settled into orbits with no special relationship to one another at all, each rounding out into its own circle, on its own schedule, each falling quiet in its own time. Instead, all 3 remain locked together, and Io, caught in the middle of that arrangement and closest to Jupiter's overwhelming gravity, has paid for it in heat ever since. Not every part of Io contributes equally to this picture, either. A relative handful of especially large, especially active features account for a disproportionate share of the moon's total heat output, while a much larger number of smaller vents and flows contribute comparatively modest amounts individually, even though collectively they add up to a great deal more. It is less like a moon evenly warmed from below, and more like a patchwork of furnaces of wildly different sizes, some roaring, most merely smouldering, scattered across a single restless surface. Nowhere on Io is that process easier to see in action than at a single sprawling feature named Loki Patera. Loki Patera is not a mountain or a cone in the way volcanoes are often pictured. It is a wide, roughly circular depression stretching across roughly 126 miles, its floor holding an active lake of molten rock rather than a single narrow vent. By surface area, that lake alone covers ground larger than Lake Ontario, and on its own, it accounts for something in the neighborhood of 1/10 of all the heat radiating outward from Io's entire surface. From a single feature among what will turn out to be hundreds scattered across the moon, Loki Patera has been watched for a very long time. Voyager 1 first photographed the feature during that same 1979 encounter that revealed Io's plumes, and the Galileo spacecraft, orbiting Jupiter for the better part of a decade, beginning in the mid-1990s, returned to study it in far greater detail. Even telescopes on the ground, here on Earth, have tracked its glow for decades, since Loki Patera radiates enough heat to be picked out against the darkness even across hundreds of millions of miles. One particularly useful opportunity arrived in 2015, when Europa happened to pass directly in front of Io as seen from Earth, briefly blocking out the rest of Io's light and letting astronomers isolate Loki Patera's heat signature with unusual precision, mapping its surface temperature in more detail than ordinary observations usually allow. Confirmation of exactly how significant this whole process is did not come from Voyager alone. NASA's Galileo spacecraft, which arrived in orbit around Jupiter in the mid-1990s and remained there for the better part of a decade, flew past Io repeatedly, each pass adding detail that Voyager's single flyby could never have captured. Galileo's instruments could linger, revisit the same features on different orbits, and track how they changed over months and years, rather than catching only a single fleeting glimpse. It was this sustained attention, orbit after orbit, that eventually allowed scientists to move from a single confirmed prediction into a genuinely detailed picture of how much heat this small moon generates, where that heat tends to concentrate, and how faithfully the mechanism Laplace, Peale, Casson, and Reynolds had described matched what a spacecraft could actually measure up close. Confirming that this mechanism worked at all, and worked exactly as predicted, mattered well beyond Io itself. Before 1979, tidal heating existed only as a theoretical possibility, a piece of orbital mechanics with no confirmed real-world example anywhere to point to. Io changed that overnight, becoming the first confirmed proof that a moon's own gravity and its neighbor's timing could power geological activity all on its own, with no help from a young planet's leftover formation heat or any radioactive decay buried inside it. Every theoretical calculation involving this kind of heating anywhere else in the solar system, in the years and decades that followed, would measure itself against Io first. Loki Patera does not glow with a constant, even light. Ground-based telescopes have tracked it brightening and dimming for decades, a rhythm scientists eventually connected to its lake's surface skin, cooling, thickening, and growing heavy enough to sink, exposing the hot, fresh material underneath, before that new surface cools in turn and the cycle begins again. Not unlike the slow, endless rising and sinking of colored wax inside a lava lamp, except carried out with actual molten rock across an area the size of a small American county. For a stretch of years, that brightening cycle repeated with almost clockwork regularity, roughly every 500 days, before falling out of step and settling into a pattern far less predictable. Even the volcano's name fits its temperament. Loki, borrowed from Norse mythology's trickster god, a fitting namesake for a lava lake that has never quite behaved the way scientists expect it to for very long. Names like Pele and Loki are not accidents of convenience. Once scientists realized how many active volcanic features Io actually had, the body responsible for approving official names across the solar system the International Astronomical Union settled on a fitting theme. Features on Io would carry the names of fire and volcano deities and figures drawn from mythologies around the world, rather than the explorers, scientists, or classical gods used to name features on most other worlds. Alongside Pele and Loki, later features would carry names borrowed from fire and volcano traditions spanning nearly every continent and era, a small reminder that a great many cultures throughout human history independently arrived at their own stories to explain fire bursting up out of the ground. Some of the material Io's volcanoes fling into space never falls back down at all. Io's own gravity is weak enough, and some of the ejected gas and dust energetic enough, that a portion of it escapes the moon entirely, drifting into the space along Io's orbital path. There, caught by Jupiter's own powerful magnetic field, far stronger than Earth's, that escaped material becomes electrically charged and forms a faint, glowing, donut-shaped ring circling Jupiter at exactly the distance of Io's orbit, a structure astronomers call the Io plasma torus. The torus itself stretches all the way around Jupiter along Io's orbital path, a glowing ring built mostly from ionized sulfur and oxygen, the same elements painting Io's own surface. Those familiar yellows and oranges, now scattered across space instead of pooled on a moon's crust. Hints that Io was doing something unusual had, in fact, been sitting in the data for decades before Voyager 1 ever confirmed any of it directly. Radio astronomers listening to Jupiter from observatories here on Earth had noticed, years earlier, that certain bursts of radio static coming from the giant planet seemed to depend on exactly where Io happened to be in its orbit at the time, a connection nobody could fully explain using the tools available then. The plasma torus, once properly identified, offered a satisfying answer. Material escaping from Io, charged and organized by Jupiter's magnetic field, was influencing the planet's own radio behavior from a considerable distance. A small moon leaving its fingerprints on its enormous neighbor's radio signature years before anyone understood why. It is, in effect, a ring built entirely from one small moon's own volcanic exhaust, replenished constantly by the same tidal engine driving the eruptions in the first place, and it stands as one more visible signature, stretched across hundreds of thousands of miles of space, of a process that begins with nothing more than two moons that never touch Io at all. All of this activity gives Io something else unusual for a body its size. An atmosphere, thin as it is. Volcanic venting constantly resupplies a wispy layer of sulfur dioxide gas hovering just above the surface, far too thin to breathe or to support weather in any familiar sense, but detectable all the same by passing spacecraft and even by telescopes here on Earth. That thin atmosphere is not even stable throughout each orbit. As Io swings behind Jupiter and passes into the giant planet's shadow, temperatures on the surface drop sharply enough that much of the sulfur dioxide gas freezes directly onto the ground as frost, thinning the atmosphere considerably, only to sublimate back into gas once Io swings back out into sunlight and warms again. A moon already being squeezed and released every 42.5 hours also spends part of each of those same orbits with its thin air freezing and thawing in step with the sunlight. Loki Patera is only one feature among a great many scattered across Io, and by itself, it can only hint at the true scale of what this endless flexing has produced. Multiply one lava lake, capable of radiating 1/10 of an entire moon's heat, by however many hundreds of similar features are scattered elsewhere across Io's surface, large and small, constantly shifting, constantly finding new paths upward, and the scale of what this mechanism has built, starts to become almost impossible to hold in mind using description alone. Words like restless, violent, or extreme can only carry a story so far before they need actual figures behind them. How many separate points of eruption exist across the entire moon? How hot the freshest lava actually runs compared to anything found on Earth? How tall these plumes climb compared to familiar heights close to home? And just how quickly, in concrete terms, this process has rebuilt a surface that shows no trace of any impact older than the last eruption to pass through it. Those figures, gathered patiently across decades of spacecraft visits and telescope observations, tell a story even more extreme than the mechanism behind them, and they are where this account has to turn next. Start with the simplest of those figures, and the one easiest to get wrong. How many volcanoes does this small moon actually have? NASA's current working estimate puts the number at roughly 400, a figure worth handling carefully, because it does not mean 400 separate eruptions are underway at this very instant. Of that estimated total, scientists have directly confirmed more than 150 as active at one time or another, catching each one in the act through some combination of a spacecraft's camera, a telescope's infrared detector, or a freshly cooled lava flow showing up where none had been photographed before. The remaining balance, bringing the total toward 400, comes from extrapolation rather than direct observation, and the logic behind that extrapolation is worth understanding rather than simply accepting on faith. Picture a large orchard, far too big for any single survey team to walk from end to end in a reasonable amount of time. If that team carefully counts every tree across one representative section, and the rest of the orchard, examined from a distance, appears to grow just as thickly and just as evenly, a reasonable estimate for the whole orchard follows naturally, long before anyone has walked every single row. Scientists studying Io have done something similar. The regions of the moon mapped in the greatest detail show volcanic centers distributed fairly evenly across the surface, with no obvious reason to expect the less studied regions to look any different. Extend that even distribution across the entire moon, and the number climbs from the 150 or so directly confirmed toward an estimated 400 in total, the great majority of which, statistically speaking, remain to be individually identified and photographed for the first time. Confirming any one of these volcanic centers as genuinely active takes patient, repeated observation rather than a single glance. Scientists look for a location that glows perceptibly warmer than its surroundings in infrared images, or a fresh, dark lava flow spreading across ground that appeared a different color in an earlier photograph, or, more dramatically, a plume caught rising directly off the surface, the way Io's very first confirmed eruption was. Each of these signs can appear and disappear over months or years, meaning the roster of confirmed volcanoes is never quite final. A feature, quiet, during one spacecraft's visit, may erupt vigorously by the time the next one arrives, and a feature, active for decades, may fall still without warning, which is part of why the running total of confirmed active volcanoes has crept upward gradually, mission after mission, rather than arriving all at once. That estimate has grown considerably over the decades, tracking each new mission's improving instruments rather than any actual change in Io itself. Voyager's original 1979 flyby confirmed only a handful of active eruptions. By the time NASA's Galileo spacecraft had spent several years studying the Jupiter system up close, that confirmed count had climbed past 80, with researchers at the time predicting the true total might eventually reach somewhere around 300 once instruments improved further. Instruments have indeed improved further since, and the number has climbed again, past 150 confirmed and toward today's estimated 400. Each increase reflects better eyes looking at the same restless moon, not a moon growing any more active than it already was. Each mission that has visited Io, in turn, brought sharper eyes than the one before. Voyager's cameras, revolutionary for their era, could only catch an eruption already large enough to rise clearly above the horizon in reflected sunlight. Galileo carried an instrument capable of mapping heat directly in near-infrared wavelengths, invisible to human eyes, allowing it to pick out warm ground even in complete darkness or obscured by distance, which is how researchers first pushed the confirmed volcano count well past Voyager's original handful. The spacecraft studying Io most recently carries an even more capable heat mapping instrument, built originally to study Jupiter's own deep atmosphere, but repurposed with remarkable success to study the volcanic moon orbiting nearby. Proof that instruments designed for one purpose can sometimes reveal far more than their builders ever intended when pointed at the right target. Two named examples help make a number like 400 feel less abstract. Prometheus, one of the volcanic centers photographed in nearly every mission to visit Io since Voyager, sits inside a caldera measuring roughly 17 miles long and 9 miles wide, large enough to swallow a mid-sized American city whole, with a lava flow spilling outward from one edge that has been tracked, drifting slowly across the surrounding plain for decades. Tavashta, named for a deity from Hindu mythology associated with craftsmanship and fire, produced a fissure eruption caught on camera by a passing spacecraft that sent a curtain of lava fountaining upward to a height just short of 1 mile. An image striking enough that scientists returned to study the same feature repeatedly in the years that followed. Prometheus has proven unusually durable by Io's standards. The lava flow associated with it has been tracked drifting steadily across the surrounding plain since Voyager's first pass in 1979, a slow-motion advance that has continued through every subsequent mission to study the moon, making it one of the longest continuously observed volcanic features anywhere beyond Earth. Tavashta's fountain, by contrast, offered scientists something closer to a single dramatic performance, its curtain of lava glowing bright enough against the surrounding darkness to be measured precisely. Before subsequent visits found the same region considerably quieter, a reminder that Io's individual features can flare up and settle down on timescales far shorter than the moon's overall volcanism ever does. Distinguishing a genuine, ongoing eruption from ground that is merely still cooling down after a recent one takes careful comparison across multiple visits. A location glowing brightly in one set of images and considerably dimmer, though still warm, in a later set is probably watching molten rock finish cooling into solid crust rather than watching a fresh eruption begin. A location that stays consistently bright across many separate observations, sometimes for years running, more likely marks a genuinely persistent lava lake or an unusually long-lived vent, the kind of feature Loki Patera and Pele have both proven to be across decades of repeated study. The heat driving displays like that runs far hotter than anything most people have ever stood near. Lava erupting on Io typically measures somewhere in the neighborhood of 1,832 degrees Fahrenheit, and some of the hottest eruptions recorded, associated with the volcano tied to Io's very first confirmed plume, have measured closer to 3,140 degrees Fahrenheit. For comparison, lava at Kilauea, one of Hawaii's active volcanoes and among the hottest, most familiar eruptions here on Earth, typically runs around 2,100 degrees Fahrenheit, itself far hotter than anything a person could survive being anywhere near. Io's lava, at its most extreme, burns roughly 1,000 degrees hotter still than that already formidable Hawaiian benchmark, a difference large enough to matter enormously for how quickly rock melts, flows, and eventually cools back into the layered, colorful crust photographed from orbit. Part of why Io's lava runs so much hotter than anything found in Hawaii or anywhere else on Earth likely comes down to what that lava is made of and what it is not. Magma on Earth typically carries a meaningful amount of water and other volatile compounds trapped within it, which tends to lower the temperature at which the surrounding rock will melt. In much the same way, a pinch of salt lowers the temperature at which ice will melt on a winter sidewalk. Io's interior appears to be far drier, with much of its original water long since lost to space, and drier rock generally requires substantially more heat before it will melt at all. The result is magma that, by the time it finally does melt and reach the surface, arrives running hotter than its earthly counterpart, almost as a simple consequence of what had to happen chemically before it could melt in the first place. That same heat has built structures that dwarf anything comparable on Earth. Some of Io's mountains rise as high as 52,000 feet, measured from base to peak, taller by a wide margin than Mount Everest, which stands 29,032 feet above sea level here on Earth. A traveler climbing one of Io's tallest peaks would climb nearly twice the vertical distance required to summit the highest point on our own planet, all on a moon barely a quarter of Earth's width. These are not volcanic cones, piled up eruption after eruption, the way many of Earth's largest volcanoes are built. They form instead through the same restless squeezing and compression driving the volcanism itself. Blocks of Io's crust shoved upward and tilted by forces acting on the moon's interior, closer in nature to a slab of ice, cracking and rearing up under pressure, than to a mountain built patiently from repeated lava flows. These mountains do not sit atop volcanoes the way most of Earth's largest peaks do. Instead, they appear to form when Io's crust, compressed from below and squeezed sideways by the same restless flexing driving the volcanism, buckles and breaks along weak points, shoving enormous blocks of solid rock upward at steep angles rather than building gradually from accumulated lava, the way a shield volcano does on Earth. Some of these tilted blocks show clear layering along their exposed faces, evidence of older material that has been thrust upward and turned nearly on its side, a visible record, even without a single impact crater anywhere nearby, that this moon's crust is under constant, immense pressure. On Earth, a shield volcano like the ones that built the Hawaiian Islands grows slowly and predictably, thin, runny lava spreading out in layer after layer over hundreds of thousands of years until a broad, gently sloped mountain rises from what was once open ocean floor. Io's tallest peaks tell a completely different story, one closer to a tectonic collision than a patient accumulation, rock shoved upward in the space of a comparatively short geological moment rather than built gradually flow by flow. Two different processes, on two very different worlds, arrive at broadly similar results. Enormous mountains, rising far above their surroundings, born from entirely different relationships between a world and its own internal heat. Working out exactly how tall these mountains stand took more than a single photograph. Scientists measured them chiefly by studying the length of the shadows they cast across the surrounding plain in images taken by the Galileo spacecraft during its extended stay in orbit around Jupiter, calculating height from shadow length, the same careful way a surveyor might estimate a building's height from the shadow it casts at a known time of day. Comparing shadow measurements from multiple images taken from different angles and under different lighting, allowed researchers to build a reliable picture of just how dramatically these peaks rise above Io's surrounding plains, tall enough, in the most extreme cases, to rival the height of features found nowhere else among the rocky worlds of the inner solar system. Mountains and volcanoes on Io are, in this sense, closer relatives than they might first appear, two different visible results of the same underlying restlessness. Where the crust buckles and lifts under pressure without finding an easy path for molten rock to escape, a mountain rises. Where that same pressure does find a crack or a weak point to exploit, an eruption breaks through instead. Some regions of Io likely experience both in close succession, a mountain block shoved upward only for a fresh vent to open along its newly exposed, fractured edge, the two processes trading places as the easiest route for all that built-up stress to release keeps shifting from one moment to the next. The plumes themselves reach heights just as difficult to hold in mind using ordinary comparisons. While the plume that first revealed Io's volcanism back in 1979 rose roughly 170 miles above the surface, later observations have caught material from other eruptions, climbing far higher still, with the faint outer edges of one especially powerful plume detected roughly 310 miles above Io's surface. A commercial airliner here on Earth cruises at an altitude of roughly 6.5 miles. Io's most powerful recorded plume climbed to a height nearly 50 times greater than that. Material thrown so far above the surface that it briefly left the moon's gravity behind entirely before falling back down as a fine, settling snow of sulfur and its compounds. A typical plume on Io rises in a distinctive shape, roughly umbrella-like, material thrown nearly straight upward from a narrow vent, before spreading outward as it reaches the top of its arc and begins falling back under the moon's own weak gravity, scattering in a wide ring around the vent that produced it rather than a single narrow line. Because Io's gravity is only a small fraction of Earth's, material launched from the surface travels far higher and spreads far wider before finally settling than an equivalent eruption ever could here at home, tracing out a pale, wide halo around the vent that can remain visible in photographs for weeks after the eruption that produced it has already quieted down. Not all of that material manages to escape Io's gravity and join the ring circling Jupiter described earlier. Most of it, in fact, falls right back down, settling across the surrounding landscape as a fine dust of sulfur and its compounds, which is precisely the material responsible for burying the moon under those 4/10 of an inch of fresh coverage every year. The relationship works both ways. Eruptions send material skyward, most of it lands again nearby and rebuilds the surface, and only a smaller fraction, the fastest moving and most energetic portion, ever truly leaves the moon behind for good. Individual eruptions, tracked in recent years by spacecraft still visiting the Jupiter system, have revealed just how much energy this small moon can release in a single event. In the closing days of the year 2024, one spacecraft's instruments picked out a hotspot near Io's southern pole, larger in area than Lake Superior, one of the largest bodies of fresh water on Earth, radiating energy equivalent to roughly 6 times the combined output of every power plant operating on this planet. A little over a year later, the same spacecraft observed something even more extreme, an eruption spreading across an area of roughly 40,400 square miles, releasing energy estimated at somewhere between 140 and 260 trillion watts, an amount of power 3 to 5 times greater than the eruption of Mount St. Helens in 1980, one of the most destructive volcanic events in recent American history. Set against Earth, the comparison becomes almost absurd. Our planet, many times larger than Io in every dimension, supports nowhere near this concentration of simultaneously active volcanic centers, despite having far more raw material and far more surface area to work with. Packed onto a body barely a quarter of Earth's width, Io's 400 estimated volcanoes represent a density of volcanic activity per square mile that no comparably sized world, and very few worlds of any size, come close to matching anywhere else that has been mapped. What made that particular eruption especially remarkable was not simply its size, but its structure. Rather than a single volcano venting on its own, instruments detected multiple separate sources erupting at once, scattered across the same general region, suggesting something scientists had not fully appreciated before. Whatever lies beneath that stretch of Io's crust may be connected in ways a single, isolated volcano could never explain on its own. Both of these discoveries came from the same spacecraft, a solar-powered orbiter that has continued studying Jupiter and its moons years longer than its mission planners originally expected, using an instrument built to detect infrared heat rather than ordinary visible light. That instrument allows scientists to measure temperature directly, distinguishing a genuinely hot, actively erupting surface from ground that merely looks dark or reddish in an ordinary photograph. It was this kind of direct heat measurement, gathered during a series of unusually close passes near Io in the years following 2022, that first revealed the scale of the southern hotspot and, later, the sprawling, multi-source eruption that followed it. Findings that would have been essentially invisible to a camera built only to see ordinary light. All of this activity, spread across 400 estimated volcanic centers and repeating without any meaningful pause, adds up to a moon that resurfaces itself at a genuinely staggering pace. Averaged across its entire surface, Io is buried under roughly 0.4 of an inch of fresh volcanic material every single year, a rate that sounds modest, described 1 year at a time, but which compounds into something extraordinary, given enough years to work with. Stretch that same rate across the span of an average human lifetime, and the entire moon would be buried under roughly 2.5 feet of freshly erupted rock and ash, an amount that would swallow a parked automobile up to its windows, spread evenly across a world larger than many countries here on Earth. Extended across a longer stretch of time, the same rate offers another way to grasp it. In the roughly 250 years since the founding of the United States, Io's volcanoes would have buried the moon's entire surface under more than 8 feet of fresh material, an amount that would bury a single-story house up past its roofline, spread evenly across a world considerably larger than the moon overhead on any given night. No single point on Io necessarily receives exactly that amount. Some regions are rebuilt far more often, others more rarely, but averaged across the whole surface, over the whole moon, that is the pace at which Io remakes itself. Even without impact craters to count, scientists can still read a rough history directly off Io's surface, using the same color-changing property of sulfur described earlier in this account. A fresh flow, only recently erupted, tends to show up dark, almost black, before gradually brightening toward yellow, orange, and eventually a paler tone, as it sits exposed to sunlight and slowly reacts over months and years. By comparing the color of a given patch of ground against everything known about how quickly that reaction proceeds, researchers can make a reasonable estimate of roughly how long ago that particular patch was last resurfaced. A rough clock written directly into the moon's own coloring, entirely independent of counting craters that, on Io, simply are not there to count. This pace of change creates a genuine challenge for anyone trying to keep track of it. A spacecraft might photograph a particular stretch of Io's surface, then not return to image that same stretch again for months or years, depending on its orbit and its other assigned duties. By the time it does return, an area that looked one way in the earlier image may be unrecognizable, buried under fresh material, its previous features gone as though they had never existed. Mapping Io in any complete sense means accepting that the map itself is perpetually out of date, a snapshot of a moon that has almost certainly changed again by the time the picture makes it back to Earth. This is why, despite orbiting closer to Jupiter than any other large moon, in a position where incoming debris should strike harder and more often rather than less, Io's surface carries not a single confirmed impact scar anywhere on it. The resurfacing happens faster than the scarring ever could. It is not unlike a chalkboard wiped clean and written on fresh every single day of a long school year, however many months that year runs. A student searching the board would never find so much as a trace of yesterday's lesson still faintly showing through beneath today's, because the erasing always finishes well before anything has a chance to accumulate. Averaged across Io's entire history, its surface carries an age of only a few million years at most, a figure almost absurdly young, set against a solar system that has existed for roughly 4.5 billion years, and against a moon that has itself existed for very nearly that same enormous span. That resurfacing rate describes an average smoothed across the entire moon, and like most averages, it hides considerable local variation. A location sitting directly above one of Io's most persistently active features, Loki, Patera, or Pele among them, likely sees its surface renewed far more often than that average would suggest, buried and rebuilt on a timescale of years or decades rather than millions of them. A quieter stretch of terrain sitting between major volcanic centers may go comparatively much longer without a fresh eruption passing directly over it, even as the moon as a whole keeps to its overall pace. Averaged across the entire surface over the entire history available to measure, the numbers hold. Examined one patch of ground at a time, the true picture is considerably less even. That comparison, a moon billions of years old, wearing a face only a few million years old at most, is not simply a poetic way of describing Io. It is a claim scientists have gone on to test directly, using a method that has nothing to do with counting craters or measuring lava flows at all. In the spring of 2024, a research team based at the California Institute of Technology, using a powerful radio telescope array in Chile capable of detecting faint gases in Io's thin atmosphere, set out to measure something almost impossibly subtle: the precise ratio of two different forms of sulfur present in the gas surrounding the moon. The telescope array used for that measurement, known by the acronym ALMA, sits high in the Atacama Desert of Chile, chosen for its extreme dryness and elevation, conditions that let its dishes detect faint radio signals from space with very little interference from Earth's own atmosphere. Measuring the ratio between two forms of sulfur floating in Io's thin atmosphere, invisible to ordinary telescopes and far too faint to detect from anywhere less pristine, required exactly this kind of instrument, one capable of picking out an extraordinarily subtle chemical signature from a world hundreds of millions of miles away. Ordinary sulfur, of the kind found throughout the early solar system, contains a predictable mix of a lighter and a slightly heavier variety of the same element, locked into place when the solar system itself first formed roughly 4.5 billion years ago. Volcanic eruptions do not treat those two varieties of sulfur equally. The lighter form escapes into space slightly more easily than the heavier one. Every time a plume erupts and scatters material into the thin, weak grip of Io's gravity, meaning that a world erupting continuously over a very long stretch of time should gradually lose more of its lighter sulfur than its heavier sulfur. Growing measurably enriched in the heavier variety, the longer that process continues. When the research team measured Io's atmosphere directly, they found exactly that kind of enrichment, and a very large one. Somewhere between 94 and 99% of Io's original lighter sulfur appears to have already escaped into space over the Moon's history. Working backward from how quickly that escape happens today, the only scenario that explains a loss that large is a moon that has been erupting in essentially this same fashion continuously for something close to its entire 4.5 billion year existence, very nearly since the solar system itself first came together. That escaping sulfur does not simply vanish once it leaves Io behind. A portion of it becomes exactly the material feeding the glowing ring of charged particles that traces Io's orbit around Jupiter, the same structure built from the Moon's own volcanic exhaust described earlier in this account. Every atom of lighter sulfur an ancient eruption has flung into space, over 4.5 billion years of nearly continuous activity, has left a measurable fingerprint in two very different places at once. A shifted ratio in the gas, still clinging to Io's thin atmosphere today, and a faint, ongoing contribution to a ring of matter stretched across hundreds of thousands of miles of space around Jupiter itself. 4.5 billion years is a span difficult to place beside anything in ordinary experience. It very nearly matches the age of Earth itself and comfortably predates the oldest rocks ever found on our own planet's surface, most of which have long since been buried, melted, or worn away by Earth's own restless geology. Io's volcanic activity, by this measurement, began before Earth had an oxygen-rich atmosphere, before life of any kind is known to have existed anywhere, and very possibly before the Moon overhead had finished forming from the debris of its own violent birth. Consider what that means, set beside everything gathered so far. Io's surface, resurfaced every few million years at most, ought to be one of the youngest-looking places anyone has ever mapped in the solar system, and by every measure gathered so far, it is exactly that. Yet the process responsible for that youthful face is, by this same measurement, one of the oldest continuously running processes anyone has identified anywhere among the planets and their moons, older than any mountain range on Earth, older than any ocean basin, present in essentially its current form, since not long after the sun itself first began to shine. A face this young, powered by an engine this old, is not a contradiction once the mechanism is understood. It is exactly what a moon caught in an unbroken, multi-billion-year gravitational relationship with its neighbors should look like from the outside, eternally rebuilt, never allowed to age, and never, in all that time, given the chance to run out of whatever is keeping it this way. This creates a genuine scientific problem, quite apart from any question of scenery. On worlds like Mars, our own moon, or even parts of Earth, scientists read deep history directly off ancient surfaces, counting craters, examining rock layers, tracing features that have survived essentially unchanged for billions of years. Io offers no such record. Its surface, however carefully studied, can only ever describe the last few million years at most, no matter how sophisticated the camera pointed at it. Anything Io's crust once looked like further back than that has been erased, melted, and rebuilt so many times over that no trace of it could possibly remain. It is precisely this limitation that made the sulfur isotope measurement described earlier so valuable. Unable to read Io's deep history from its ever-changing surface, researchers instead read it from the Moon's thin atmosphere, a record kept not in rock, but in the shifting proportions of gas escaping into space, the only kind of clock this particular moon had left running. None of this settles the deeper question sitting underneath all of it. Knowing that Io generates enormous heat, and knowing that it has done so for nearly the full span of the solar system's existence, still leaves open exactly what that heat is doing once it leaves the outer layers of rock and reaches whatever lies farther down. Is there a single, continuous layer of molten rock wrapped around the moon's core, a genuine ocean of magma feeding every eruption from below? Or is the truth closer to what that January eruption, with its several separate sources acting almost in coordination, seemed to hint at? Not one connected reservoir, but countless separate pockets of melted rock, each one its own small furnace, scattered throughout an interior that is otherwise closer to solid than anyone expected. Every figure gathered so far, the volcano count, the temperatures, the mountain heights, the plume heights, the resurfacing rate, describes what reaches Io's surface or escapes it entirely. None of it, on its own, can see through solid rock to the layer generating all that heat in the first place. Scientists studying Io today are still working out which picture is closer to the truth, and the most direct evidence yet gathered on that question did not arrive from counting volcanoes or measuring their heat at all, but from something far stranger, watching, with extraordinary precision, exactly how much this entire moon flexes as it completes each and every orbit. Watching how much an entire moon flexes from a spacecraft racing past it at tens of thousands of miles an hour sounds like an impossible thing to measure directly, and in one sense, it truly is impossible. Nobody points a camera at Io and watches it visibly bulge and relax. Instead, scientists rely on something almost every person has experienced without ever thinking of it as a scientific instrument: the changing pitch of a sound as its source moves toward you or away from you. The same effect that makes an ambulance siren sound higher as it approaches and noticeably lower as it speeds off into the distance. A spacecraft's radio signal behaves exactly the same way. As gravity speeds a passing spacecraft up or slows it down by even the smallest amount, the radio waves it sends back to Earth shift in frequency by a correspondingly tiny amount, and listening stations here on Earth can measure that shift with extraordinary precision, track those shifts closely enough across a close enough pass, and the spacecraft's own changing speed becomes a direct readout of exactly how strongly and how unevenly gravity is pulling on it during that flyby, which in turn reveals how mass is arranged inside the body it just passed. The precision required to make measurements this fine defies easy comparison. Scientists tracking the spacecraft's radio signal during these flybys could detect changes in its speed of a fraction of a millimeter per second, roughly the speed of a fingernail slowly growing, extracted from a signal that had already traveled hundreds of millions of miles by the time it reached a listening station here on Earth. That level of sensitivity is what allowed Io's gravitational fingerprint, however faint, to stand out clearly enough from the background noise of ordinary orbital motion to be measured and trusted. Io is not the only place in the outer solar system where this same underlying mechanism does its work, though it is very much the most dramatic example of it. The same tidal flexing that keeps Io's interior partially molten also reaches Europa, the smooth, ice-covered moon introduced earlier in this account, and a moon of Saturn's called Enceladus, a small, icy world discovered to be actively venting material of its own. On Io, dry and rocky and squeezed hardest of all four inner moons by its tight orbit around Jupiter, that flexing melts stone. On Europa and Enceladus, built instead from a thick shell of ice wrapped around a rocky core, the very same kind of internal flexing does something gentler but no less remarkable. It keeps a layer of liquid water from freezing solid, sandwiched between the ice above and the rock below, not unlike the way a pond here on Earth can freeze into a solid sheet on its surface each winter, while the water underneath, insulated from the worst of the cold, stays liquid the whole season through. Different material, different result, the same essential physics running underneath both. Enceladus offers the clearest visible proof of that hidden ocean. Enceladus first revealed this hidden ocean in dramatic fashion in 2005, when a spacecraft studying Saturn's system flew close enough to photograph towering jets of water vapor and ice erupting from cracks near its south pole. Plumes climbing so high above this small moon, barely 300 miles across, that they could be traced clearly from orbit, and were later flown directly through and sampled by that same spacecraft. Chemical analysis of that material has revealed traces of salts and organic compounds consistent with a genuine liquid ocean in contact with rock below, warmed and kept from freezing by tidal flexing, driven by Enceladus's own gravitational relationship with a larger neighboring moon named Dione, playing a smaller scale version of the same role Europa and Ganymede play for Io. Europa is suspected of hiding an even larger ocean beneath its own ice, one that may hold more liquid water than every ocean on Earth combined, though its icy shell has so far kept that ocean's contents from erupting as visibly or as dramatically as Enceladus's plumes do. Europa in particular is about to receive far closer scrutiny than Io currently allows. A dedicated mission named Europa Clipper, launched in the fall of 2024, is now making its way toward Jupiter's system with the specific goal of studying that moon's suspected ocean in far greater detail than any previous spacecraft has managed. Arriving sometime toward the end of this decade, where Io's harsh radiation environment has limited spacecraft to brief, carefully timed passes, Europa sits just far enough from Jupiter to make a longer, more sustained study feasible, meaning the coming years may answer questions about Europa's hidden ocean with a level of confidence Io's own interior structure may still be waiting for. Ganymede, already familiar from earlier in this account as one of the two moons whose timed gravity keeps Io's orbit from ever settling into a calm circle, turns out to play a second, entirely different role in this same broader story. Ganymede itself is suspected of hiding a saltwater ocean of its own, sandwiched between layers of ice deep beneath its ancient, grooved surface. Warmed by a gentler version of the same tidal squeezing it helps impose on Io. The same moon contributing to Io's fire, in other words, appears to be quietly running a smaller version of the very process it helps drive in its neighbor. The difference between a moon that erupts fire and moons that hide frozen oceans instead comes down largely to what each one started with and how much of it survived. Io almost certainly formed with some amount of water and ice of its own, much like its neighbors. Sitting closest to Jupiter and subjected to the most intense tidal heating of any of the 4 Galilean moons from very early in its history, Io likely lost whatever ice it once carried long ago, boiled away, and lost to space before the moon ever settled into the dry, rocky world observed today. Europa, orbiting farther out and heated more gently, kept enough of its original ice to maintain a thick shell of it even now. Enceladus, tiny and cold on the surface despite its own hidden warmth, has held onto its ice more easily still. 3 moons, similar origins, and 3 very different outcomes, shaped as much by distance and history as by the tidal mechanism they all still share. Set beside one another, these 3 worlds tell a broader story about how a small body, far from any star's warmth, can still stay geologically alive. None of them are heated in any meaningful way by sunlight, which arrives at Jupiter roughly 1/27th as strong as it does here on Earth, and weaker still by the time it reaches Saturn. None of them generate meaningful heat through their own radioactive decay, being too small to hold much of that kind of warmth for long. All 3 depend entirely on the same gravitational relationship with their neighbors, the same relentless squeezing and releasing described earlier in this account, to stay warm enough, in whatever form that warmth ultimately takes, to remain active rather than freezing into permanent, unchanging stillness. Io simply represents what that process looks like when it happens to a small, dry, rocky world instead of an icy one, heat with nowhere gentler to go than straight through solid stone and out into space as fire, rather than as a hidden, quiet ocean. Accounts like this one are, in a sense, always slightly out of date the moment they are finished, a reflection of exactly the same restless quality driving the moon they describe. The measurements covered here, the 2024 gravity result and the newer temperature result alike, represent the best available understanding at the time this account was prepared, not a final verdict closed permanently to revision. Further flybys, further analysis, and further disagreement among the scientists studying this small moon should all be expected, not as a sign that anything described here was wrong, but as the ordinary, healthy way understanding of any genuinely active area of science continues to sharpen over time. Everything gathered across this account, the plume Linda Morabito found by accident in a photograph nobody else was watching closely, the precise, timed relationship between 3 moons that keeps that plume and hundreds like it endlessly renewed, the scale of mountains and lava and heat that numbers alone can only partly capture, and now this newest, still unfolding picture of what lies just beneath Io's restless skin describes a single continuous story rather than a series of separate discoveries. Each new measurement has not replaced what came before it, so much as added another layer of resolution to the same underlying picture, the way a photograph slowly comes into sharper focus without ever fundamentally changing what it depicts. Return, for a moment, to the very beginning of this account, a small moon, painted in colors unlike anything else, photographed up close, carrying not a single confirmed scar from a wandering piece of debris anywhere on its entire surface. That absence of scars once looked like a puzzle with no obvious answer, a moon that, by every ordinary rule governing small, cold worlds, should have gone quiet and still billions of years ago. It has not, and by now, the reason is no longer a mystery, even if some of the finer details remain genuinely unsettled. Io's violence is not the sign of a world coming apart, burning through some final reserve of heat on its way toward a quiet ending. It is the visible signature of a relationship that has held steady for nearly the entire life of the solar system. 3 moons locked into a rhythm precise enough that not one of them has ever been allowed to simply settle down, Io paying the largest share of that arrangement's cost in heat and in fire and in a surface that never gets the chance to grow old. Earth's own restlessness, by comparison, moves at a pace almost too slow for a single human life to notice. Mountains rising a fraction of an inch a year, continents drifting more slowly than fingernails grow, entire mountain ranges taking tens of millions of years to rise and wear away again. Io compresses that same fundamental restlessness, the ordinary, unglamorous business of a world managing its own internal heat, into a rhythm fast enough to unfold across a single human lifetime many times over, repeating on a schedule measured in hours rather than eons. It is the same basic story every geologically active world tells, simply narrated at a dramatically different speed. There is something worth sitting with in that, once the mechanism behind it is fully understood. 4 centuries of watching this small corner of the sky, stretching from Galileo's first glimpse of an unexplained point of light beside Jupiter to a spacecraft measuring heat rising through solid rock from hundreds of millions of miles away, have not resolved every question Io raises, and were never going to, not on the timescale of a single human life, or several. None of that remaining uncertainty changes what Io has actually been doing, quietly and without pause, the entire time anyone has been watching, and for a very great span of time before anyone was. Stability, in this particular corner of the solar system, does not look like calm. It looks like a moon that has never once been permitted to rest, squeezed and released, roughly 200 times over with every single year that passes, for longer than Earth has had continents in anything resembling their current shape. What looks from a distance like catastrophe, endless eruptions, mountains taller than any on Earth, a surface rebuilt over and over without pause, is not evidence of a world in crisis at all. It is simply what permanence looks like. For a small moon caught this close to a planet this large, held in an arrangement this old, somewhere out past Mars tonight, that same small moon is still glowing, still being needed by forces it will never escape and, by every indication gathered so far, was never meant to sleep now. Some small worlds work through the night so you don't have to.